In this video, we're going to look at what's called a piecewise function. So this is where on different pieces of the function will be differently defined. So in other words, on a certain part of the domain, the function will follow one formula, and on a different part of the domain, it will follow a different formula. And then you could have as many of these pieces as we want. So let's just take a look at a simple example first. So this is how we would write this, the notation. So we write f of x equals, and then we put a left brace, but a bit of a larger brace, so that we know that all of this is part of the function. So maybe we say that the function is equal to 2 if x is greater than or equal to 0, and negative 2 if x is less than 0. So a couple of key points here. First of all, notice that in our case, we've accounted for every possible x value. And you don't have to do that, but in this case, our domain is going to be negative infinity to infinity because we have defined every single possible x value. Also notice that at x equals 0 specifically, this is the point where the function is changing, right? The equation of the function is changing, and only one of these sides should be equal to 0. We can't have both of them equal to 0 because then we would have 2 points at 0, which would make us fail the vertical line test and therefore not be a function. Okay, so these are some important things to keep in mind here. So what this function would look like, okay, if we graph it, and maybe we could go ahead and make an XY chart actually. So if any of our points, so let's do 0, 1, 2, negative 1, negative 2. So any point that's greater than or equal to 0 will fall under the first part of the function, and it'll be 2. And then any point that is less than 0 will fall under the second part of the function, and then it will be negative 2. So 0 itself falls under the first part, so this output is going to be 2. And then same with 1 and 2. Negative 1 and negative 2 are less than 0, so they're going to follow the second part of the function, so it's going to be negative 2. So this is going to be a constant function at 2 on the right side, meaning from 0 onwards, right? So this is what it will look like over here. Now on the other side, the rest of the graph is going to be from negative 2, it's going to be a constant function at negative 2 from every point that's less than 0. Now notice that this function is going to go all the way up to x equals 0. It's not, the negative 2 part is not going to touch at x equals 0, but if you put in, say, negative 0.0001, it would still be negative 2, right? So we need to go all the way up to 0. So the way we represent that is with what we call an open circle, which is exactly what it sounds like, an open circle. Okay. So the open circle means we go all the way up to this point, but we don't actually have a point there, right? So we do have a point defined at x equals 0, but it's all the way up here, right? It's at 2 instead of down here at negative 2. So this is what the graph would look like. Okay, so it's a piecewise function because on the piece where x is greater than or equal to 0, it's defined as 2, and it looks like this. And then at on the piece where it's less than 0, it's negative 2, and it looks like this, right? So your graph can have different jumps in it. So notice the range here is a little bit weird, right? It's going to be, if we want to, we could write it with the set notation, right? Just write negative 2 and 2. That would be fine. If we want to do it with the interval notation, we would write this as negative 2 to negative 2 union 2 to 2, which is a little bit strange, but that's what we would have to come up with here. But when it's just a couple of points like this, it's probably more common just to write it as a set and just list the points out. Okay. So let's look at some other examples of piecewise functions. A very common one is actually the absolute value function. So if you remember, this is the function that takes any value and makes it positive. We can define this as a piecewise function, because if x is greater than or equal to 0, this function is simply f of x equals x, right? It doesn't, the function doesn't do anything to the value if it's already positive. So if the function is, or if the input is 1 or 2 or 3, it simply leaves them alone, right? Now, if you put a negative number into this function, then it's going to make it positive. So how would it do that? Well, if there's a negative input, it's going to need a negative on it in order to cancel out the negative on the input, right? Because 2 negatives will cancel out and leave you with a positive. And so it'll end up looking like this, right? Negative x. So if we plug in negative 2, for example, f of negative 2, this would be negative, negative 2, and the negatives cancel and leave us with positive 2. Okay. So we already saw this graph on the parent graph video, right? So it looks something like this here, where it's symmetric along the y-axis, even though it doesn't look like it from my drawing, but it should be. Right, so this is an alternative way to write the absolute value function. Okay. Now, in both of these, we've only had 2 pieces, but we can have as many pieces to the function as needed. Okay, so we just do another example here, maybe just make this up off the top of my head here. Okay, maybe we have x squared if x is greater than 2, 3 if x is between, let's go negative 1 is less than or equal to x is less than or equal to 2. Okay. Maybe it's equal to x if x is less than or, sorry, just less than negative 1, but greater than, I don't know, 3. Maybe then it's equal to, sorry, this should be negative 3, right? Maybe it's equal to the absolute value of x if x is equal to 3. And then finally, it's equal to, let's say the 1 over x if x is, sorry, this again should be negative 3, right? So if x is less than negative 3. So we have 5 pieces here. Let me make this a little larger to encompass all of it. So it can be a big behemoth like this is, right? It doesn't just have to be 2 pieces. So in order to graph this, we want to plug in points from every one of the pieces here and kind of use our knowledge of the parent graphs to help guide us in the shape. Okay, so some of the easy ones first. If x is between negative 1 and 2, it's just going to be equal to 3, the constant function. So at negative 1, it's 3. At 2, it's 3. And everything in between is 3. If x is greater than 2, then it's equal to x squared, right? So if we put in 3, for example, it's going to be 9. So 4, 5, 6, 7, 8, going off screen here a little bit. 9. Okay, so at 3, this is equal to 9. Now, again, on the x squared part, it's going to go all the way up to 2 or down to 2, but it's not actually going to touch 2. So it's still helpful to know what this limit is, right? So maybe you put in like 2 in quotes, right? Where you're not actually putting in 2, but you're seeing where that x squared function is going to end up at, right? Which is 4. So in other words, we're going to have an open circle at 2, 4, which is going to be this graph here, which is kind of like an extreme curve. Okay, so now less than -1, but greater than -3, the function is equal to y equals x. Okay. So let's say this is for the x squared piece. So for the x piece, right, we'll have this chart a little squished here. So again, at -1, to see where this function is going up to, this would be -1. So we have an open circle at -1, -1. And then same with -3. We have an open circle at -3. And then there's going to be a straight line in between here because this is a linear function. So that's what I mean about our knowledge of the parent graphs kind of guiding us here. Okay, so now at 3 itself, it's simply going to be, or at -3 itself, it's simply going to be 3, right? Because the absolute value of -3 is 3. So looking at this piece now, at -3 itself, we get this. Okay. And now finally, below -3, can kind of remember the parent graph of the 1 over x, where it's getting closer and closer to 0, but never touching 0. It'd be a good idea to plot a couple of these points, and also think about where our open circle is going to be right at when this function is approaching -3. Where is it going to? So plugging in -3 in quotes, right, we get -1/3. So at -3, -1/3, there's an open circle. So this open circle is important because we can't have more than one point at x equals -3, right? Even though we're looking at 3 different points here, 2 of them aren't actually on the graph. And then from that point on, it's just going to get closer and closer to the x-axis. So using that knowledge of the parent graph here. But you can plug a couple points in here too, right? -4 will give you -1/4, for example. And so this is what the graph ends up looking like, right? Not a, very pretty graph, not a very nice shape, but that's what it is. The domain, believe it or not, all real numbers, right? Every x value is accounted for here. We made sure of that. Unless I missed one, but it doesn't look like it, right? Everything looks good. There's always a closed circle or point somewhere, right? This should be going to infinity. I didn't make that clear, right? Like that's going to keep increasing. So there should be an arrow on the end of it. But yeah, so everything is good there. The range, however, we do have some pretty serious gaps here. Very serious gaps, right? And we can kind of use our points that we plotted to help guide us here. So we can see between 3 and 4, there is a gap. Let's start from the negative infinity side though, right? So going from negative infinity up to what is this point? This is -3, right? From our y equals x part here. There's nothing there. So our range is going to start at -3, but not include -3. And it's going to go up to -1, not including it, union. Then there's going to be a gap up to this point right here, which is -1/3, this open circle. And then it's going up to 0, but neither of these are included because it's not touching -1/3, it's not touching 0. Now we're jumping all the way up to 3, which is included. And we're only hitting that point because that's a constant function. And now I'm running out of room here, so I'll scroll up and down. You can see that there's a gap between 3 and this point, which is 4, this open circle. So we're going to go up to 4, but we're not including 4. And then it keeps going without a problem all the way up to infinity. Okay, so it's going to look like this here. -3 to -1, neither included. Union -1/3 to 0, neither included. Union 3 is included. Union 4 to infinity, neither included.